Hello and welcome. In this presentation, we see topic 6, where we look at design of generalized functional observers for the following time delay systems. Now, this time delay system has this extra delay term in the output measurement vector. Okay, so we have this extra term in there. And the output measurement vector, we call it y tilde. And y tilde is a function of the instantaneous output measurement, the linear combination of the output measurement vector, and it delayed output measurement vector. The generalized functional that we want to estimate is given by this functional, where we have this delay term in there as well. When we look at this class of time delay system, the only difference between this system and the one that we consider in topic 5 is the extra delay term in there. Now, the reason for addressing this problem actually comes from the metric decomposition, the unknown input decomposition of this class of time delay system. So for this class of time delay system, we have a delay stack vector in the output measurement vector. And as we discussed previously, that was done in topic 4, part 3, where we look at the decomposition for the unknown input. And then we need to make an assumption about the structure of the matrix CD. We want it to be 0. And because of this 0, either of the following conditions hold. And the first one is this conditions, V1 CD is 0. So there is a constraint on the output matrix CD in which the first row of it has to be 0. And this is a simplified condition which give us this condition equal to 0 as well. And therefore we obtain the decomposition where we got a reduced order time delay system with a delay term in there, and also the generalized functional. Okay, so that's where it came from. And so we need to design a generalized functional observer to estimate this generalized functional for this time delay system. Of course, this is a new problem. This is a new problem which has not been reported in the literature, because we are dealing with generalized functionals as well as a delay in the output measurement vector. Now, since we define this problem, which we want to address, of course, there are other methods that can be applied, or we can come up with some other new methods and so on to solve this problem. What we do in this book is we're going to propose a structure for this generalized functional, and it's similar to the one in topic 5, part 1. It's a kind of similar structure. This structure here, because of the delay in the output measurement, and therefore we also have this extra term in there, but that's it to counteract the multiple delays in the output measurement. The approach that we're going to do, we adopt the same approach. as in topic 5, part 1. So in other words, we going to define an error vector, which is the difference between the estimation of this generalized functional and itself. Oh, by the way, that should be an X bar in there. Okay, that should be an X bar in here because that is the generalized functional which is defined in here. So we adopt the same approach because it's a pretty easy, straightforward. This same approach from the previous topic can be easily applied to solve this problem. That's why we adopt it, even if there is an extra delay term in the stack vector in the output measurement vector. We can address it in a unified way. All right, so the approach in here is define error vector, which is the difference between the estimated one and the actual one, and then taking its derivative with respect to time, and ensuring that the error vector goes to 0 or time goes to infinity, in the same way as that we done in previous topic. So the detail is skipped here, and the reader can actually go through the whole process of doing that, taking the differentiation of both sides of this expression respect to time, and then substitute what is the estimation of the generalized functional, and then more substitutions and rearranging them and group them into line terms and all of that, similar to the one that we did in here. All right. It's straightforward, by the way. It's just a little bit tedious to do. And the key things that we like to present in here is that we can ensure the error goes to 0 if this error time delay system is stable. That's what we call equation 1. The other observer parameters are associated with the output and delay output of this equation, which is these stuff here, and the observer structure with containing these unknown parameters associated with the output measurement vector and its delays and so on. Those can be easily obtained, which are expressed in its entirety here. And they are depending on the unknown metric M, MD. So if M, MD are known, then the rest of them can be obtained. That's why they are not that really, we are not really concerned about them because they can be obtained once the observer parameters M and MD are found. The other conditions, we now have 4 matrix equations, actually 4, instead of 3, as in the previous topic. In the previous topic, we have this metric condition equation related to x bar 1 of t, and so we have 3 metric equations. And that's why we got these 3 matrix equations. Now, because of the delay in the output measurement vector y tilde t, we got that c tilde d1, which is non-zero. That gives rise to another equation. So that gives another equation. And that another equation is basically this equation here that corresponds to x bar 1 t minus 3 tau. So in here we got up to t minus 2 tau, but now in this situation we go up to x bar 1 t minus 3 tau. So in summary, it's a very relatively easy to derive the existence conditions for this observer based on the same approach that we adopted in topic 5, part 1. By the way, this approach is based on our original framework we did earlier, and that was based on this reference by Nam, which is the reference given in here. Okay, so we in topic 5, part 1, when we derive the existence conditions, we follow a similar framework at this method in here. And in this problem here, when we consider generalized functional for this class of time delay system, we also adopt the same framework, the same approach there. We arrive at an extra metric equation, four of them. But however, it doesn't cause us any additional difficulties at all, because we can easily stack the four metric equation together to form a global augmented oval metric equation. So when we examine these matrix equations, we have the same number of unknown matrices, and D, T tilde, M, W tilde, MD, and U tilde. And the right-hand side terms, these are from known matrices. Yeah, so that's associated with F and the time delay A bar, the metric A bar 1 1, and all of that. These are known terms. So we then also the rest of the metric line is all defined accordingly to like in the previous one. So that's the proof for obtaining the existence conditions expressed in here, and we just omit them because this can be done. All right. So what would like to focus on is the solution, the necessary and sufficient condition for the existence of the solution of these four metric equations. That's what we are interested in. And that can be done fairly easily as well. So we stack them together and we form this new matrix. Now, when you look at this new matrix, we actually have four columns here, four column matrices here, in contrast to the previous problem where we had only three there, only three. The reason why we have four is because we have four matrix equations, four matrix equations to satisfy. So we got four columns there. And have a look at them carefully. We can see that the FD matrix is actually entered into this matrix here. This FD is included, as well as C tilde D1. C tilde D1 is the one that associated with the delay stack vector in the output measurement. Right, and also we define another matrix which is called C tilde 1A. C tilde 1A is the sum of these two terms with involved with this C tilde D1 as well. So when we look at this big matrix here, we can see that it has 1, 2, 3, 4, 5, 6, 7 block rows, and it has four columns. block columns. It corresponds to 4 metric equations. And there's 7 block rows corresponds to these 7 unknown observer matrices. And likewise, this metric here is associated with the right-hand side terms of the 4 metric equation. Again, they are known. F, FD, and all of that. So when we look at this, this is a fairly unified framework in dealing with generalized functional observer. For any kind of time delay systems, actually, here, this is the time delay system with a delay vector in the output measurement. So we can adopt this same approach here to solve. Firstly, we come up with an observer structure. This observer structure cell contain an internal delay term and multiple instantaneous delay output measurement vector, as well as in here it also include a delay output measurement vector. So this observer structure in itself is the one that we came up with. We could include more terms in there, but when we have more terms in there, whether it's necessary or not, that is a result of a careful consideration. In this presentation, we propose this structure, which is fairly general enough to demonstrate the method, the estimation of the generalized functional. And of course, if we make this term 0, then it becomes an observer without an internal delay. And in that case, the aerodynamic equation depends on n, matrix n only. And if n is stable, then it will be independent of the time delay. So we got these 4 matrix equations that we need to solve for. And we have the necessary and sufficient condition, which is this condition. You will find that it pop up all the time when we are dealing with the generalized functionals, because this is the necessary and sufficient condition for the existence of a solution, which is this unknown matrix here. This is the augmented unknown matrix. It guarantees the system. It doesn't guarantee that the observer is stable. All right, so that's the important bit. To guarantee that the observer is stable, we have to obtain a solution. And as I discussed previously, maybe we should come up with another condition to ensure that the error time delay system is stable. But that, again, that involves solving error mine of that stuff. Which is why we didn't present that second condition. We only present the if and only if condition for the systems. And then when we say, all right, if it's satisfied, we can then follow in like the rest of the analysis, just like this topic, get the general expression for the solution. And if this term here is non-zero, that might give us an extra degree of freedom in assigning the stability of the time delay system. Or in other words, we might need to solve the stabilization problem of finding this matrix Zi here, where we have N1 and N2 are known, ND1 and ND2 are known. So we might need to search for this unknown matrix in order to stabilize this observer error time delay system. And if we find it, then that will then be put back into here, and then we obtain the final solution for X. If we don't have a time delay or unknown without internal delay, sorry, then we just have this bit here. And of course, we can have a condition to ensure detectability or observability of that pair. So that's where I discussed in the previous talk. That is something that the reader can investigate. Now, So as far as this presentation here, we say that, look, we're going to obtain this big matrix, and then this matrix as well, and then we test this condition. And when we test this condition, if it's satisfied, then we go ahead and solve for it, and then look at the stabilization of the time delay system, or ensuring that we can find a stable metric n. And then if it's satisfied, the rest of the observer parameters can be obtained. And that's why we just don't want to delve into that again, just repeating the same thing. The other thing that we like to say in here is when this metric is 0, in other words, again, the observer itself is the one without internal delay. We can then test the following condition, which is a reduced matrix, where we remove ND, which means that this block row here is removed. And of course, that gives rise to a more conservative condition. But then the price that we can gain from here, or the reward, is an observer without internal delay. Okay, so in summary, as far as the problem of design a generalized functional observer to estimate this generalized functional for this class of time delay system, it can be done. We have presented the observer structure for it. We also presented an approach for deriving the assistant conditions, and we presented the assistant conditions. The key to that is the solution of these 4 matrix equations to ensure that this error time delay system is stable. Okay, so it boiled down to that 2 issues. Of course, the first thing is the solvability of these couple metric equations. They are linked to the if and only if condition, which is the one here. And if this one is holds, then we proceed to solve for the unknown matrix, taking into account the extra degree of freedom in the solution of this generalized metric equation, which is the one expressed in here. And if it is possible to stabilize the observer error dynamic equation, then the rest of the parameters can be obtained. Okay, so that's basically the discussion for design generalized functional observers to estimate the generalized functional of this time delay system. If we examine this matrix here, we can see that we got this delay matrix FD, the delay output matrix C tilde D1 in there as well. The fact that we have extra equation means that there are more columns now in this matrix. So there are more columns than the previous one. The previous condition, we had only 3 times n minus 1 columns. Here we got 4 times n minus 1 columns. Every column block here has n minus 1 columns. So when we have this situation, what it tells us is, look, the condition is more conservative. All right, the condition is more conservative because what happened in here is we have more columns than before. And of course, there is every chance that this matrix here is a row matrix. In other words, the number of rows would normally be less than the number of columns. Like, for example, you got only, if you have less output measurements, then when we look at the number of rows in this matrix, it is more or less a row matrix. And then because in here we also have additional rows on by adding this augmented with this matrix. So most of the time when we have only a few functionals that we want to estimate, and the number of output measurements is small, normally this condition does not satisfy. Okay, this condition normally does not satisfy or might not satisfy depending on the problem that we are looking at. And in that case, this is because the extra number of columns that resulted in this matrix here, and that came from this bit here. So that tells us that, look, if we have a time delay system with delay output measurements, or in other words, the output measurement vector contain this delay stack vector. It is a much more difficult problem than the one that we consider in here. Okay, so that is the difference there. That is the thing that we pay attention to that. Of course, the way that we solve and obtain the conditions of adopting the same approach, this doesn't cause any difficulty in the approach itself, but the actual outcome is that the one with the delay stack vector in the output measurement is normally more conservative. And that leads us to an example. All right, so we're going to consider an example. And this example is the one that we presented in chapter 13. I don't know where that is, let's look for it. So this is the discussion regarding the situation where the matrix C tilde is not zero. And that's exactly what we've been going through so far. And so we come up with this observer structure, and then we got the conditions. And then now we're looking at an example. And in this particular example, we re-look at the one that we did in the previous example in chapter 4, example 6, where we were looking at the design of a delay stack variable for the case where this term equal to 0. Okay, so this is for the case where this term equal to 0. Now we don't have it 0 anymore. We have it non-zero. So that related to the problem, the system that we specified here. And where that came from, it actually came from the decomposition where we look at a class of time delay system with a delay term in here. And so that also came from this numerical example. This numerical example where now we got a CD is no longer 0, but look at the structure of CD here. It's had this constraints imposed on it. And this constraint imposed is because we want to ensure the following condition, which is this condition in here. And because V1 is of a specific structure which has the non-zero element in this first entry and the rest of them 0. So we want it to be 0. The first row of matrix CD has to be 0. All right, so when it comes to the estimation of the unknown input for time delay system with this term in there, we look at the constraint number 1 here. All right, so So the example that we are taking in here is from example 1, chapter 5. And when we do the decomposition, we actually have this C tilde D1 is non-zero. And we still arrive at the unknown input, which is expressed in its entirety, where we take the first derivative of output measurement 1 and its measurement 1 and its delay measurement. But we have this extra bit here. And this extra bit is the generalized functional, which is estimating only the delay stack variable in there. So X bar 1, 2 delay, just like in our example 6 in chapter 4, we need to estimate it directly. Okay, so the metric F and FD is basically 0, 0, and 0, 1. Okay. So in this example, that's exactly that. And since we got the conditions, we got the observer structure, so we can easily carry on with the process to realize a generalized functional observer for this time delay system with C tilde D1 non-zero. And we want to estimate this particular generalized functional where we estimate the delay X bar 1, 2 directly. So what we do is we say, okay, we go through the process. We first do the one without internal delay, because that gives us the seamless structure. Now, the issue that we are facing in here is similar to the one in the example 6 in chapter 4 previously. That is, we're going to get an unstable observer. So we get an unstable observer with a fixed pole at 1. That's just to tell us that, look, when we are dealing with a class of time delay system with the output contained in the delay stack vector, it's a more conservative problem. Okay, so this is what we explain in here. We first try to do it, but then we get an unstable system, unstable one. And then that's exactly what we've been telling. So we increase the order observer or what to do. Now that is also a problem that remains to be solved. So what we say in here, okay, now the first order without internal delay doesn't work. So what the next option available? So the next option available is an observer with an internal delay. Why do we have to do internal delay for this? The reason is that when we actually do the one without internal delay and we do it higher order, we face the issue with an observer fixed mode, just like in the previous one. But this is the case for C tilde D1 not zero. So there are an alternative way to look at an observer with an internal delay. All right, so if we do that, this is exactly also the conditions that we're going to apply. We see the one in here. So we have a row here. We have this row in there. And with this row in there, that means that we include ND in there. So we have the codings for that. This is the one that say first order with an internal delay. So we substitute all of that in. And then we're going to just show that we can actually search for a matrix we call Z to ensure that the time delay error dynamical system is stable. Now, what we do in here is, let me explain it a little bit by bit. So we solve for the solution. We solve for the solution. And when we solve for the solution, we obtain the matrix. What is it called? We call it X here. And the freedom we have in there, we call ZH. So let's look at X here first. This one is the one that include the bit in here, which is the one that does not have that extra freedom. So we call that X there. And when we look at that, we can see that this is N1, which is unstable. And this is ND1, this second one, ND1. So in other words, the time delay system itself has N1 there is an unstable bit. ND1 is the minus sign. And then we also have this extra freedom from this expression. And that came from ZH. Okay, so when you look at the first column here, the first column of this matrix, that is the matrix N2. And when we look at the second column of that, it's called ND2. So in other words, we have some sort of arbitrary extra column in here that enable us to stabilize the time delay system, time delay error system. And because this one here, we just simply, we explain in here, we just simply we just pick a non-zero element from there. So we arrive at the following error time delay system. Okay. Now notice that the first bit is N1, which comes from this solution here, 0.55. And the next one is minus 0.45. So that's exactly what's happened in there. So, and then the bit in here, we just pick a single non-zero element from there because N2 and ND2, they're exactly the same, which what we can see from here. ZH, look at the first two columns there, they're actually identical. And so the problem is the following. How do we stabilize this time delay system for a given tau? Now, in this example, we did it for a time delay equation equal to time delay equal to half a second. So we basically facing with the stabilization problem. Can we find a value for A with a given tau to ensure stability of this error time delay system? The answer is yes, it can be done. It can be done. And it can be done based on the exact stability condition given in this reference. There are a number of ways to do, and here I just pick a value I equal to -3. The reason for that, when I pick I equal to -3, the conditions given by this reference is satisfied. By the way, we can also work out what is the maximum value of the time delay tau to ensure stability as well. So that is another thing that we can do. But bear in mind that for this error time delay system, it can only be stabilized for up to a certain range of time delay. So that's where we discussed previously. In the previous problem, the stabilization was there is just a fixed constant equal to 1, and there is a gamma. If you can remember that particular problem, don't know where it is now, but there was that particular problem in there, I think it's chapter 13. Yep. Example 1. Whereas in this situation, we can relax that aerodynamic equation a little bit. A little bit. So like when we look at example 1, we discussed it before, and we say that look, the error is in this thing is it's actually more conservative, Whereas in this example, even though we got an unstable fixed mode at 1, but by using our the solution, we arrive at an aerodynamic equation which is less conservative, or it can work for a wide range of time delay system. Let's put it that way. Okay. So in here, this is the thing. And so I just pick I equal to -3. I could have picked it somewhere different, but it still can also arrive at a stable time delay system. So the main thing here is it depending on the time delay, because this is the aerodynamic equation. It's a time delay system. Okay. Now, if we pick the value for I, and that's where we obtain where it is. That's where we can get the solution for the observer. Okay, so we internal delay. Yeah, this is the bit. And then we pick the value of I to be 3. Yeah, -3 there. And that's give us this observer. So we can still design a first order observer with internal delay to estimate the delay stack variable directly. Okay, to estimate the delay stack variable directly. And remember, this is the situation where the matrix C tilde D1 is no longer 0. It's not 0. And this is the example for chapter 5, example 1. So we got the observer parameters, and when we run it, we can have a look here. We got the metric N, -0.8, the metric ND, -1.8, and M, and so on. So we done the design of a delay stack observer to estimate directly. Okay, to estimate directly. And it's an observer that use the internal delay. So it's an observer. It's a bit more complex, but it's still a first order observer. It's still a first order observer. Because of the additional constraint that the matrix C tilde D1 imposed onto the observer design. And as I discussed before, we got extra columns and all of that stuff in there. So we still managed to design a first order observer with an internal delay to estimate the delay stack variable directly, and we use it to reconstruct asymptotically the unknown input. All right, so let's have a look at the thing there. We already done the simulation. We already done the code in there. Now this is how it can then be incorporated into the estimation of the unknown input. Okay, so this is the codings for chapter 5, example 1. We got the metric A, ID, D, C. Remember, CD is now non-zero matrix, and our decomposition allows us to obtain the matrix C T1, C tilde 1, C tilde D1, and the metric F and the FD. And then now we use the one with internal delay. That's why when you look at that row in there, that is for the one with an internal delay. So the condition itself, as you can see, it contains 4 block columns. And that is the one with ND not equal to 0. And so we have a stable observer error dynamic equation, which is a time delay system. And then we obtain the rest of the parameters, and we can verify all the conditions, which what we done in here. Let's clear this. And let's paste that in. And so we can see that all the conditions are satisfied. We got 4 of them, 1, 2, 3, 4 of them. And this one is the one that checking the rank condition. Okay. So that checking the rank condition in there. And that's why when it's satisfied, we get the solution. And then we do the stabilization. We just pick the value of I to be 3 in there to get an observer aerodynamic equation, which is basically that one there. And it's stable. Okay. And then we obtain the rest of the observer parameter, and we can verify the conditions, like 4 equations in there. And now we then show that, look, it can then be used to realize the asymptotic estimation of the unknown input using this generalized functional observer to estimate the delay stack variable directly. And there you go, just bang it in there. And we obtain a simulation results. And this simulation results is basically telling us that, look, when we apply this observer to example 1 in chapter 5, the estimation of the unknown input asymptotically estimate the true unknown input. We see these simulation figures in here. And that is for the first example of chapter 5. You see the one given in this simulation figure here. Okay. Now, let's see, it's from MATLAB. There, that's the simulation figure itself. We observe in here that the time it takes for the estimation of the unknown input to convert asymptotically to the true unknown input takes a little bit longer time. As you can see that taking something like about 4 seconds. The reason for that is because the observer that we design, the aerodynamic equation itself is in terms of an aerodynamic observer, which is minus 0.8 and minus 1.8 ET minute tau. In contrast to the previous one, we had an observer which we can arbitrarily assign the dynamics of the error, which is n itself, and the pair is observable. Remember that? And at that time, we could place it anywhere we like. So the conversion of the asymptotic estimation of the unknown input for this problem is actually slower than the other problem, the other case. All right, because of this situation here. This error here is basically estimating it with this error dynamics here. Okay, so if we look at the simulation for example 6 scenario 4, which is this one, you can see that it's asymptotically convert to the true estimation quicker. All right. But as far as asymptotic conversion is concerned, well, this is the thing that we can do for this situation, for this example 1, chapter 5. All right, so that conclude the discussion of the design of a generalized functional observer to estimate this class of time delay system where we got this delay term in the output measurement vector. Now, I would like to re-emphasize the fact that this is a new problem. Okay, this is a new problem that has not been reported in the literature. The way we solve this problem is based on a very standard framework where we propose the structure, where we define the error vector, and we derive the observer conditions, existing conditions. And then we work out the if and only if condition for the existence of the observer parameters. And then if it is satisfied, then we can look for the stability of the desired observer. And we took an example to demonstrate the case where this metric is non-zero. In contrast to the previous example where it is 0, the observer first order without internal delay does not exist. That's just to show that the additional difficulty in having this term in our model, okay, in our time delay model. But luckily for us, we can ensure stability of the observer error dynamic equation by designing an observer with an internal delay. Of course, it doesn't work for all time delays, but in this case, we pick a delay which is small enough, and it is okay to achieve that. Now, in the next video, we can still continue on this topic. Okay, we continue on this topic, which is topic 6, part 2, where we would like to take another numerical example. We want to take another numerical example to demonstrate the generality and significance of generalized functional observers. Now, in the next discussion, we're going to consider a time delay systems and with C tilde D1 not 0 and all of that stuff. But when we demonstrate that we can insert more rows into the desired observer, we could range from a second order observer, or we can also have a third order observer. How about that? We couldn't even have a third order observer without internal delay. Now, bear in mind that the system itself, as given in here, is a second order time delay system because basically they have two cycle variables in there. So I would just basically call it second order system. To estimate a particular generalized functional for it, we show how it can be done. We also explore different structures, how to go about inserting a row to satisfy certain condition, and what are the options available. Do we go for second order system with an internal delay, line option 1 here, or do we go for a higher order observer without an internal delay? And that is the discussion that we're going to do in the next talk. And that will cover enough of evidence to tell that when it comes to generalized functional observers for time delay systems, we can have more options available if we adopt the kind of generalized functional the problem that we address in this new book. Okay. So thank you very much for watching, and I hope that you can join me again in the next video. Thank you.